Welcome to the Joy of Architecture. Today, we're embarking on a deep dive into an organization that's really become, well, foundational for modern software and infrastructure. The Cloud Native Computing Foundation, or CNCF.
Yeah, absolutely foundational.
Think of this as your essential guide, maybe a shortcut, to understanding this vibrant world that powers so much of what you use every day. You know, streaming services, complex enterprise apps, all that stuff.
Exactly.
We'll try to uncover how it all started, how it's organized, and the powerful tools and patterns it's championed.
Right. Our mission today is really to equip you with the knowledge to navigate this, let's face it, pretty complex ecosystem. We'll show you not just what these technologies are, but crucially, why they matter for the future of software development and, how they solve real-world architectural challenges you might be facing.
We've got a fantastic stack of sources to guide us through this, so let's just jump right in.
Let's do it.
So where does it all begin? Let's start with the very essence of the CNCF itself. How did this whole thing get going?
Well, the Cloud Native Computing Foundation, it was formed back in 2015. It's actually part of the Linux Foundation.
Okay.
And its core mission is pretty bold: to make cloud native computing ubiquitous. What's really interesting, I think, is its design. It's set up as a vendor-neutral open source ecosystem.
Vendor-neutral, that's key.
It absolutely is. It fosters a huge amount of trust and, crucially, prevents any single company from kind of dominating the direction of these really critical technologies.
And its origin story is fascinatingly tied to one specific technology, isn't it? Came out of the gate strong.
Absolutely. It was announced concurrently with the 1.0 release of Kubernetes.
Ah, Kubernetes.
Right. Google contributed Kubernetes as the CNCF seed technology.
Yeah.
And that immediately positioned Kubernetes as like the gravitational center.
Right.
The initial group of founding members included giants, Google, Red Hat, IBM, Intel. It showed this collective industry investment right away, and that structure provides a really stable foundation for collaboration, and it significantly mitigates those vendor lock-in risks for organizations like yours.
Okay, that brings up a really core question then. What exactly do we mean by cloud native? Because it feels like it's more than just, running stuff in the cloud.
Oh, definitely. You're right to ask. And the CNCF actually provides a formal definition. It's sort of part mission statement, part architectural blueprint.
Okay.
It defines cloud-native technologies as those that empower organizations, like yours perhaps, to build and run scalable applications in these modern dynamic environments. Public, private, hybrid clouds, doesn't matter.
So what does that look like in practice?
Think of it in terms of like key building blocks and philosophies. You've got architectural primitives.
Like containers.
Exactly. Containers, packaging components for reproducibility, and microservices, breaking apps into small, independent services for agility.
Right.
Then there are the operational paradigms. This is how you manage it all.
Okay.
So dynamic orchestration tools like Kubernetes, actively scheduling and managing containers, and immutable infrastructure. This is a big one. You treat infrastructure components as disposable.
Right. Build new instead of patching old.
Precisely. Build new. Don't modify old ones. It drastically cuts down configuration drift. And also declarative APIs, managing systems by declaring the desired state in config files, not issuing step-by-step commands.
Got it. And the outcome of all this?
Well, the system-level outcomes these primitives and paradigms enable are things like resilient systems that tolerate failure because they're loosely coupled. Manageability automation reduces the operational burden. And observability systems designed from the ground up to give you deep insights via metrics, logs, traces.
So it really is a whole operational philosophy change, not just adopting containers. But, okay, with what, over 200 projects now, how does an architect even begin to navigate this world? It sounds overwhelming.
It can seem that way, but that's where the CNCF interactive landscape comes in.
Okay.
Seriously, think of it as your essential map.
Okay, a map. I like that.
Yeah, it organizes projects into logical columns, different layers of the stack: provisioning, runtime, orchestration and management, app definition, observability, platform. Projects have to meet criteria to even get on there, like 300 GitHub stars. And the landscape gives you dynamic metrics too, like project velocity, contributor counts. It's a living, breathing guide for evaluating technology. Really useful.
Okay, so this huge ecosystem obviously needs strong governance. How does this CNCF make sure these projects are actually stable and reliable enough for, real enterprise use?
That's a great point. They use a dual governance model, which is quite smart. It separates the business side from the technical side.
How does that work?
So you have the governing board, or GB. They handle the business stuff, budget, marketing, legal things. Importantly, They don't make technical decisions for the projects.
Okay, so who does?
That's the Technical Oversight Committee, the TOC. This is the technical heart. It's made up of senior technologists from across the industry.
Right.
Their job includes defining the technical vision, approving new projects, overseeing their life cycle, how they mature, and establishing common practices. This dual structure gives you checks and balances, ensuring technical integrity and that crucial vendor neutrality.
You mentioned maturity. One of the most valuable things, I think, are those project maturity levels. How should someone listening use that framework? How does it guide decisions?
Oh, this is absolutely critical for adoption decisions. The CNCF classifies projects into 3 main levels: sandbox, incubating, and graduated. And these map really nicely onto the innovation adoption lifecycle.
Okay, break those down for us.
Sure. Sandbox is the entry point. Early stage experimental projects. Think high innovation, but also high risk.
So maybe for R&D, not production.
Exactly.
Yeah.
Use sandbox projects like, say, OpenCost or K0s for research and development, proofs of concept. You probably wouldn't bet your main production systems on them just yet.
Got it. What's next?
Incubating. These projects are demonstrating real viability. They need documented adoption by at least 3 independent end users running them in production.
Okay, so they're getting traction.
Right. Projects like Linkerd, Istio, Argo, Cilium, they were all here before they graduated. These are generally suitable for production, but you still need a bit of comfort with being an early adopter. There might still be rough edges.
And the top tier.
That's graduated. This is the highest level of maturity. These projects are stable, they're battle-tested, they have widespread adoption across different industries. They're considered enterprise grade.
Like Kubernetes itself.
Precisely. Kubernetes, Prometheus, Envoy, Helm, etcd, remember, etcd, and OpenTelemetry are all examples. They've usually passed formal security audits, have broad community support. They're solid.
So for an architect listening.
For you, the architect, this is basically a formal risk assessment framework. Adopting a graduated project. High degree of assurance. Choosing an incubating project. It's viable, but be prepared. Sandbox. That's a significant, but hopefully accepted, risk you're taking for experimentation. There's also an archive state for inactive projects, by the way.
That's really helpful. It's amazing how it's all powered by, over 24,000 individual contributors? That's a huge community.
It's massive. Truly a testament to the open source model.
Okay, let's dive into some of those core technologies then. The ones that really form the foundation of this cloud-native operating system, as some call it. The real workhorses.
Exactly. And it's important to see them not just as separate tools, but how they integrate to form this cohesive platform.
Okay, first up, got to be the undisputed king, Kubernetes.
No question.
Yeah.
Kubernetes is that foundational layer. People often call it the kernel for distributed systems, and it's a good analogy.
Right.
It automates deployment, scaling, management of containerized applications. Architecturally, you've got a control plane, the brain-managing worker nodes that actually run your applications.
What's in the control plane?
Key components are the API server, which is the front end, and talks to etcd.
The brain's memory.
It's exactly. etcd, the consistent key value store, the source of truth. Then there's the scheduler for placing workloads, and the controller manager, which works to reconcile the current state with your desired state.
And the workers.
Worker nodes run the kubelet, an agent that makes sure containers are running, kubeproxy for networking rules, and the container runtime itself, like container tune.
So what are the key use cases for an architect thinking about Kubernetes?
Oh, loads. Microservices deployment is the classic one. CI/CD automation becomes much smoother, building portable apps that can run across different clouds or on-prem, and increasingly running AML and big data workloads. Adoption is nearly universal now. Google, AWS, Microsoft, Apple, Spotify, you name it.
So if Kubernetes is the kernel, what's our top command? How do we monitor it?
Good question. That would definitely be Prometheus. It's the de facto standard for metrics-based monitoring in this world.
How does it work? Is it push or pull?
It's primarily a pull-based model. The Prometheus server scrapes metrics endpoints exposed by your services or by exporters that translate metrics. It stores this data in its own time series database, TSDB.
And querying.
That's done using PromQL, a really powerful query language specifically for time series data. Then there's the alert manager, which handles alerts defined in Prometheus, grouping them, routing them to Slack or PagerDuty or whatever. There's also a push gateway for short-lived jobs that can't easily be scraped.
What are the common patterns for using Prometheus?
Monitoring Kubernetes cluster health itself is huge. Application performance monitoring, too. A really effective pattern for you is observing the 4 golden signals of service health: latency, traffic, errors and saturation. Lots of big names use it. SoundCloud, DigitalOcean, Uber.
Okay, next on the core list, Envoy, the universal data plane. Sounds important.
It really is. Envoy is a high-performance, programmable L4, L7 proxy. Think of it as the network substrate, especially for service meshes. It abstracts the network away from your applications.
How's it designed?
Its core design is running out of process, usually as a sidecar container alongside your application container. It's fundamentally a byte proxy, but it has this pluggable filter chain architecture that allows for really sophisticated traffic manipulation.
And it updates easily.
That's its killer feature. Dynamic configuration through what are called XDS APIs. This allows control planes to update Envoy's configuration, routing rules, policies, etc. without needing to restart it. Huge for availability.
So what are its main roles?
Two primary roles stand out. First, as the service mesh data plane. It intercepts all the traffic going in and out of your service, enforcing policies set by a control plane. Second, as an edge proxy or API gateway, handling ingress traffic coming into your cluster. Lyft originally developed it, now Google, IBM, and crucially, major service meshes like Istio are built on top of it.
Right, managing all these Kubernetes apps, definitions, configs, it can get really complex. How does Helm help simplify things?
Helm is essentially the package manager for Kubernetes. Think after Yum for Linux, but for K8's applications.
Okay, so packages.
Exactly. The core concepts are the chart, which is the packaging format, basically a collection of files describing Kubernetes resources. A deployed instance of a chart is called a release, and charts are stored and shared via repositories.
What makes a Helm chart powerful?
Its structure. You have chart.yaml for metadata, values.yaml for default configuration parameters, and then a templates directory with Go templates. These templates generate the actual Kubernetes manifest files. When you install or upgrade a release, it allows you to parameterize your deployments.
So it's the standard way to...
It's become the standard for packaging, sharing, deploying, and managing the lifecycle of even complex Kubernetes applications and their dependencies. Really indispensable.
Okay, you mentioned etcd a couple of times as Kubernetes source of truth.
Mm.
Let's just double-click on that, make sure we get the pronunciation right, and really understand its critical role.
Yes, absolutely. It's pronounced etcd.
Yeah.
And it is foundational. It's the distributed key value store that Kubernetes relies on entirely for storing its state. Its design priorities are consistency and availability above all else.
How does it achieve that consistency?
It runs as a cluster, typically 3 or 5 nodes, and it uses the Raft consensus algorithm. Raft ensures all nodes agree on operations. It works by electing a single leader node, and any write operation requires acknowledgement from a majority of the nodes before it's considered committed. This provides strong consistency, even if some nodes fail or the network gets flaky.
And its role specifically within Kubernetes.
The Kube App Server is the only component that talks directly to etcd. All other components go through the API server. This means if your etcd cluster goes down or its data gets corrupted, well, your Kubernetes cluster state is effectively lost.
Wow. Okay.
Yeah. That's why operational best practices are so strict. You need fast, low-latency storage like SSDs for the etcd nodes, reliable network connectivity between them, regular backups. It's the heart of the cluster.
Got it. Okay, finally, on the core observability front, OpenTelemetry, or OTel, sounds like it's aiming to unify everything.
That's definitely the ambition. OTel is an observability framework. Its goal is to standardize how telemetry data that traces metrics and logs is generated, collected, and exported. It actually merged 2 earlier projects, OpenTracing and OpenCensus, to provide a single vendor-neutral standard.
How does it work architecturally?
There are a few key parts. You have the API and SDKs, which are libraries developers use to instrument their application code. Then there's the collector. This is a really important piece. It's the vendor-agnostic proxy.
A proxy for telemetry.
Yeah, think of it like that. It has a pipeline architecture. It uses receivers to ingest data in various formats, processors to batch, filter, or add attributes to the data, and exporters to send the data off to different backend systems, like Prometheus or Jaeger or a commercial platform.
So it decouples your instrumentation from your backend.
Exactly. That's a huge benefit. It also has its own native wire protocol, OTLP, Open Telemetry Protocol, which is designed to be efficient.
What's the primary pattern for architects using OTel?
The main pattern for you is creating that unified observability pipeline using the collector. This gives you the flexibility to change or add observability backends later without having to go back and re-instrument all your services. It saves a ton of effort.
And its most powerful use case?
Arguably, it's enabling distributed tracing across complex microservice architectures. Understanding how a request flows through multiple services is incredibly difficult without it. OTel makes it feasible to pinpoint bottlenecks and errors in those distributed systems. And, if we sort of step back and look at these graduated projects together, Kubernetes, Prometheus, Envoy, etcd, OTel, you start to see a powerful recurring pattern.
Oh, yeah. What's that?
The separation of the control plane from the data plane. Kubernetes separates its control plane, the brain, from the worker nodes, the data plane. Envoy is designed as a pure data plane configured by an external control plane. OpenTelemetry uses the collector as a kind of processing and control layer for the telemetry data plane.
That's interesting. Centralized intelligence managing distributed work.
Precisely. It's a pattern that allows for scale and centralized management of distributed systems. It's something you should definitely consider leveraging in your own architectural designs.
Okay, so those are the stable, graduated foundations. But the cloud-native world, it never stops evolving, does it? What's bubbling up in the incubating and maybe the high-velocity sandbox projects? What's solving those next-generation problems?
Right. This is where you see the future being forged. These projects are often tackling the second-order problems that arise, precisely because the foundational layer, like Kubernetes, has been so successful.
One of the biggest debates, or at least architectural choices, seems to be around the service mesh. Let's talk about Linkered versus Istio. What's the core trade-off there?
Yes, the service mesh decision. It's a really crucial architectural trade-off, and it basically boils down to simplicity versus power, or feature set.
Okay, tell me about Istio first.
Istio is designed as this comprehensive, feature-rich platform, kind of the Swiss Army knife of service meshes. It uses the very powerful Envoy proxy under the hood, which we just talked about. It offers extensive traffic management capabilities, fine-grained security controls, multi-cluster features, lots of knobs to turn.
Linkered.
Linkered takes a different approach. It follows a more minimalist philosophy. It focuses laser-sharp on the core service mesh value propositions, security, especially MTLS, observability, and reliability, but prioritizes operational simplicity. It uses its own purpose-built microproxy written in Rust, which is known for performance and safety.
So how does this difference play out for an architect making a choice?
It has direct consequences for you. In terms of performance and resource usage, Linkered's Rust proxy generally shows lower latency and consumes less memory compared to Istio's Envoy, which is more feature-packed but heavier.
Interesting. What about security?
On the security posture, Linkered really emphasizes zero config mutual TLS, MTLS, right out of the box. It aims to make secure communication the default and easy. Istio offers more granular security controls, which can be powerful, but it also brings higher configuration complexity.
And the feature set.
Istio definitely has a broader feature set. Things like advanced routing rules, fault injection for chaos engineering, sophisticated multi-cluster setups. Linkered focuses on hitting, say, the core 80% of common use cases really well with less complexity. So you really need to candidly assess your organization's actual needs. Do you need all the bells and whistles Istio offers? If you only need basic MTLS and observability, choosing Istio might saddle you with significant operational overhead you didn't need. It's a classic complexity versus capability trade-off.
That's a great breakdown. It's fascinating how these projects themselves embody architectural patterns. Speaking of which, what about Argo? What's its role as the so-called GitOps champion?
Argo, and specifically Argo CD, has really become the de facto standard for implementing the GitOps pattern. It's fundamentally a declarative, pull-based, continuous delivery system designed for Kubernetes.
How does it work? Pull-based, you say?
Yeah, that's key. Argo CD runs as a Kubernetes controller inside your cluster. It continuously monitors a Git repository, which you designate as the single source of truth for your desired application state. Its application controller component watches for any difference between the state defined in Git and the actual live state in the cluster.
And if it finds a difference?
It automatically reconciles the live state to match what's in Git. This embodies the core GitOps principles. Your desired state is declarative, defined as code, usually YAML in Git. It's versioned and immutable. Because it's in Git history, it's pulled automatically by an agent inside the cluster, which is generally more secure than push-based CI systems needing credentials to the cluster. And the state is continuously reconciled against drift.
So the CI pipeline just updates Git?
Exactly. Your CI pipeline builds the image, maybe runs tests, and then its final step is updating the Kubernetes manifests or Helm chart values in the designated Git repo. Argo CD picks it up from there and handles the deployment within Kubernetes. There are different deployment patterns for Argo CD itself, too. You might have a centralized hub-and-spoke model managing many clusters, which simplifies management but creates a potential single point of failure or security blast radius. Or you might run standalone per cluster instances, which offers better security isolation but means more operational overhead. Big companies like Intuit, the New York Times, BlackRock are using it at massive scale.
Okay, and then there's Cilium. It leverages this Linux kernel technology, eBPF. What on earth is eBPF and why is it making such waves?
Right, eBPF, Extended Berkeley Packet Filter, is, I'd argue, one of the most disruptive and exciting technologies in the infrastructure space today. It's fundamentally a way to run small, sandbox programs dynamically within the Linux kernel itself, without changing kernel source code or loading kernel modules in the traditional sense.
Run programs in the kernel. How does that help?
It enables unprecedented capabilities in networking, observability, and security because you can safely inspect and manipulate system behavior at the kernel level with very low overhead.
And how does Cilium use it?
Cilium leverages eBPF heavily. Architecturally, it has an agent on each node that manages the eBPF programs loaded into the kernel, an operator for cluster-wide tasks, and a component called Hubble for network observability, which is also powered by eBPF.
What does it do with eBPF?
Primarily, Cilium provides a high-performance CNI container network interface for Kubernetes networking and enforces network security policies based on identity rather than just IP addresses. But here's where it gets really interesting for architects.
Go on.
Cilium is presenting a major architectural alternative to the traditional sidecar-based service meshes, like Istio or even Linkerd, with its sidecarless service mesh capabilities.
Sidecarless.
By using eBPF programs in the kernel, Cilium can intercept and manage network traffic directly. This means it can potentially provide L7 traffic management, like HTTP routing, observability, like gathering metrics, and security features, like transparent encryption, without needing to inject a separate proxy container, the sidecar, into every application pod.
Wow, that sounds like it could have big performance benefits.
That's the promise. Potentially lower resource overhead, CPU and memory, compared to running a sidecar proxy everywhere, and maybe simpler operations since you don't have to manage the sidecar injection and lifecycle. Major cloud providers like Google Cloud, with GKE Data Plane v2 and AWS, are adopting Cilium, along with big users like Adobe and Datadog, precisely because of this unique architecture and the performance benefits eBPF brings. It makes the service mesh choice even more interesting. Now, it's not just Istio versus Linkerd, but also sidecar versus sidecarless with Cilium. Crucial trade-off for you to evaluate.
Absolutely fascinating. Okay, so beyond these individual powerful projects, it really sounds like the CNCF ecosystem as a whole has codified a set of common architectural patterns that people can learn from and apply.
Exactly. And mastering these patterns gives you, as an architect, a really durable mental model for designing and reasoning about complex distributed systems. They transcend specific tools.
Let's talk about some of those. What about cloud-native reference architectures? Is there a standard blueprint?
Well, the CNCF End User Technical Advisory Board, so actual users of this stuff, distilled some essential attributes that well-architected cloud-native systems should have.
Like what?
Things like being distributable, meaning built from loosely coupled microservices. Observable, having monitoring, tracing, logging built in from the start. Portable, avoiding tight coupling to specific cloud provider services where possible. Interoperable, using language-agnostic APIs. And crucially, available design for resilience against component failures. You should definitely use these attributes as a high-level design guide or checklist for your own systems.
Okay, and we talked about GitOps with Argo, but let's solidify that as a pattern itself.
Right. GitOps has really emerged as the definitive pattern for continuous delivery in the cloud-native world. Its core principles, as we saw with Argo CD and also championed by Flux, another graduated CNCF project, are key. Your system state apps, infrastructure, everything is declarative, defined in a machine-readable format. It's versioned and immutable because it lives in Git, giving you that crucial audit trail and rollback capability. Changes are pulled automatically by an agent running within the cluster, which improves the security posture. And that agent continuously reconciles the live state against the desired state in Git, automatically correcting drift. It's a powerful operational model.
Makes sense. And the service mesh pattern. We touched on it with Istio and Linkerd, but how does it specifically help manage that complex service-to-service communication in a microservices world?
Yeah, as soon as you break your monolith into microservices, the network between them becomes incredibly complex and critical. The service mesh pattern introduces a transparent infrastructure layer specifically to manage this communication complexity.
Usually with sidecars, right?
Yes. The most common implementation uses a lightweight sidecar proxy, like Envoy or Linkerd's Rust proxy, deployed alongside each instance of your application container. This sidecar intercepts all the network traffic going into and out of the application.
And what does that achieve?
The crucial thing is it decouples network logic from application logic.
Yeah.
Your application developers don't have to build retry logic, complex routing, or encryption into their service code anymore. The mesh handles it transparently in the sidecar.
So what capabilities does the mesh provide?
3 main areas. Traffic management, things like dynamic routing for canary releases or A/B tests, automatic retries, circuit breaking to prevent cascading failures. Security, arguably the biggest win, automatic mutual TLS, MTLS, between services, providing authenticated and encrypted communication by default. And observability, the sidecars are perfectly positioned to collect consistent metrics like those 4 golden signals, latency information, and generate the data needed for distributed tracing. It also typically standardizes how you manage traffic entering the cluster, ingress, and leaving the cluster egress through dedicated gateway components. It brings order to the network chaos.
Okay, and finally, the observability pattern, the 3 pillars. Remind us what those are and why they're essential together.
Right. Observability is critical for understanding why something is broken in these complex distributed systems, not just that it's broken. The 3 pillars are metrics. These are numerical measurements aggregated over time. Think counters, gauges, histograms. They give you the overall health picture. What Prometheus is the key tool here. Logs. These are time-stamped records of discrete events that happened. They're crucial for forensic debugging, understanding the specific sequence of events leading to an error, the detailed why. Traces. These track the path of a single request as it propagates across multiple services in your distributed system. They're essential for pinpointing bottlenecks and understanding the latency contributions of each service in a transaction, the where. OpenTelemetry is key for enabling this. And the real goal, the pattern you should strive for, is to unify these 3 pillars. You want to be able to correlate them easily. For example, embedding trace IDs into your log messages allows you to jump directly from a specific trace showing high latency to the detailed logs for just the services involved in that trace. It allows you to seamlessly pivot from an alert on a metric, the what, to the traces showing which service path is slow, the where, to the specific logs explaining the error, the why. That correlation is incredibly powerful for troubleshooting.
That makes perfect sense. Okay, it's one thing to talk about these amazing technologies and patterns, but how are real organizations actually putting them to work? What are the tangible benefits they're seeing?
That's where the rubber meets the road. Right. The CNCF website actually prominently features case studies, and they show significant business outcomes.
Can you give us some examples?
Sure. In networking and security at scale, companies like Datadog and Trip.com Group are leveraging Cilium and eBPF for high performance, secure networking in very demanding environments. For GitOps and continuous delivery, look at Love Holidays. They use Argo CD to manage thousands of deployments across their clusters, executing something like over 1,500 production deployments monthly. Imagine the velocity gain. Or Babylon Health, using Argo CD combined with Kubeflow for ML pipelines, reduced the time for clinical validation of models from 10 hours down to under 20 minutes. Huge impact. And for service mesh and API gateways, Domino's Pizza UK and Vonage use Envoy-based solutions like Glue Gateway to manage their complex microservice communication effectively. What these cases really show is enterprises are not just adopting single tools, they're composing multiple CNCF projects together into these cohesive platforms to solve systemic challenges around scale, security, and importantly, developer velocity.
That mention of platforms leads perfectly into the exciting rise of platform engineering. What exactly does that entail in this cloud-native context?
Platform engineering has become a really hot topic, and for good reason. It focuses on building what are called internal developer platforms, or IDPs.
IDPs, what are?
An IDP is essentially a curated set of tools, services, documentation, and automated workflows that your platform engineering team provides to your internal application development teams. The goal is to give developers a smooth, self-service, paved road experience for building, deploying, and running their applications.
So abstracting away the complexity?
It's exactly. It aims to reduce the cognitive load on developers. They shouldn't need to be Kubernetes experts or networking gurus just to deploy their service. The IDP abstracts away the underlying cloud-native complexity, letting them focus on writing code that delivers business value. And CNCF projects are absolutely central to building effective IDPs. Backstage, which is a graduated project originally from Spotify, has become the de facto standard for building developer portals the front door to your IDP. And Crossplane, an incubating project, is powerful for building cloud-native control planes that can provision and manage infrastructure across different cloud providers through the Kubernetes API.
It sounds like a crucial role.
It really is. The CNCF even recognized its importance by launching a new certification, the Certified Cloud Native Platform Engineering Associate, CNPA. That's a strong signal about where the industry sees value.
Okay, so we have this vibrant open source ecosystem. How do the major cloud providers like AWS, Google Cloud, Azure fit into this picture? How do they align with the CNCF, and what does it mean for that whole Kubernetes distribution debate?
That's a really important strategic consideration. The major cloud providers heavily embrace and validate the CNCF stack, primarily through their managed Kubernetes offerings, EKS on AWS, GKE on Google Cloud, AKS on Azure.
So they're built on the same core tech.
Yes, they are generally conformant upstream Kubernetes distributions. But using them brings a critical architectural trade-off you need to weigh. Managed services like EKS, GKE, AKS. The big pro is they offload a significant amount of operational burden patching the control plane, managing etcd, etc. The con is you typically have less control over the underlying infrastructure, and there's always the potential for vendor lock-in to their specific ecosystem features built around Kubernetes.
Right. What are the other options?
Then you have vendor distributions like Red Hat OpenShift or SEC Rancher. These are often hardened, opinionated platforms that bundle Kubernetes with a whole suite of other tools, networking, monitoring, CI/CD developer tools into an integrated solution. The pro is that integrated experience and support. The con is usually licensing costs and, again, potential lock-in to that vendor's ecosystem.
In the third way.
The third way is DIY upstream Kubernetes, just taking the open source code and running it yourself on VMs or bare metal. The pro here is maximum flexibility, zero vendor lock-in. The massive con is you bear the full burden of operations, security, upgrades, everything. It requires significant in-house expertise. So for you as an architect, this isn't just a technical choice between distributions. It's a fundamental strategic decision. You have to balance how much operational heavy lifting you want to offload versus how much control and flexibility you need to retain. The great thing about the CNCF is that it ensures those open source, vendor-neutral projects remain a viable alternative, keeping everyone honest.
That makes a lot of sense. Now, in such a dynamic, distributed environment, security has got to be absolutely paramount. How does the CNCF approach the unique security challenges that cloud-native architectures present? Traditional models don't quite cut it, do they?
You're absolutely right. Traditional perimeter-based security models, the old castle and moat approach, are largely insufficient when you have workloads spinning up and down dynamically, communicating across complex networks. Cloud-native security needs to be built in from the start, it needs to be continuous, and it needs to be much more identity-aware.
Okay, so what are some of the core security projects within the CNCF that help achieve this?
Two really key graduated projects here are Falco, an open policy agent, or OPA.
Tell me about Falco first.
Falco is essentially a cloud-native runtime security tool. Think of it like a security camera for your infrastructure, detecting anomalous activity in real time as it happens.
How does it do that?
It observes system calls directly from the Linux kernel using either traditional kernel modules or increasingly eBPF probes, or it can consume Kubernetes audit logs. It then runs these events against a set of customizable rules you define. If an event matches a rule indicating suspicious behavior, like unexpected network connections, sensitive file access, privilege escalation attempts, Falco generates an alert.
Okay, so runtime detection, what about OPA?
OPA, Open Policy Agent, is different. It's a general-purpose open-source policy engine. Its core idea is to decouple policy decision-making from policy enforcement.
Decouple policy.
You write your policies in a declarative language called Rego. Your application or service then queries OPA whenever it needs to make a policy decision, like, is user Alice allowed to access resource X? OPA evaluates the relevant policies against the input data and returns a decision, allow Johnny. OPA itself is the policy decision point, PDP, while your service is the policy enforcement point, PP.
How is OPA used in the Kubernetes world?
Very widely. A common pattern is using it as a Kubernetes admission controller, usually via a project called OPA Gatekeeper. This allows you to enforce policies before objects are even created or updated in the cluster. For example, you could enforce policies like all deployments must have resource limits set, or all ingress objects must use HTTPS. It's also used for API authorization within applications.
That makes sense. Beyond runtime security and policy, securing the software supply chain itself has become a huge focus lately, hasn't it?
Oh, absolutely. It's critical. And the CNCF hosts key projects in this area, primarily SigStore and the SLSA framework.
What does SigStore do?
SigStore is actually a suite of tools and services designed to make cryptographic signing of software artifacts, container images, binaries, configuration files easy and ubiquitous. The goal is to be able to verify the integrity and origin of software effortlessly.
How does it work?
It leverages a few components. Full CO acts as a certificate authority that issues short-lived code signing certificates, cleverly tied to existing OpenID Connect identities, like your GitHub or Google login. Record provides a public immutable transparency log where signatures and attestations are recorded. Think of it like a tamper-proof ledger. And cosign is a command line tool that makes the process of signing artifacts and verifying signatures much simpler for developers.
Okay, and SLSA. I hear that pronounced salsa.
Yes, SLSA, supply chain levels for software artifacts, pronounced salsa. It's not a tool, but a security framework or specification. It provides a checklist of standards and controls designed to prevent tampering, improve integrity, and secure the artifacts throughout your software supply chain, basically, from source code to the end user.
How does it work? Levels, he said.
Right. SLSA defines 4 progressive levels of assurance, from SLSA Level 1 up to SLSA Level 4. Each level adds stricter requirements. Level 1 might just require verifiable provenance metadata about how an artifact was built. Higher levels require things like hermetic, hardened builds happening in isolated ephemeral environments, ensuring the build process itself is trustworthy. For you, SLSA offers a practical roadmap for incrementally improving the security posture of your CI/CD pipelines. You don't have to boil the ocean day one.
That's really useful. How does all this runtime security, policy, supply chain security tie into the broader concept of zero trust architecture? It feels very aligned.
It's perfectly aligned. Zero trust architecture is a security model that essentially shifts from the old trust but verify mindset to never trust, always verify. No user, device, or workload is trusted by default, even if it's already inside your network perimeter.
What are the core principles?
Verify explicitly based on identity and context. Use least privilege access. Give entities only the permissions they absolutely need. And assume breach. Design your systems assuming attackers are already inside. And in a cloud-native context, you implement these principles using exactly the kinds of CNCF projects we've been discussing. You achieve identity-centric security using service meshes like Istio or Linkerd for automatic MPLS between services, perhaps combined with PIFBuyer for workload identity. You implement microsegmentation using Kubernetes network policies, often powered by CNIs like Cilium, or fine-grained L7 policies within a service mesh. And you enable continuous monitoring and validation using tools like Falco for runtime threat detection and OPA for enforcing access policies dynamically. It's about moving security away from the perimeter and embedding it deeply at the application and identity layer.
That makes a lot of sense. Okay, shifting gears slightly, the real power of these CNCF projects often comes from how they integrate together, forming a seamless end-to-end platform. How do these core projects connect with adjacent domains, like, say, CI/CD?
That integration is key. CNCF projects are absolutely central to modern CI/CD pipelines. We already talked about Argo, particularly Argo CD for GitOps delivery, but the Argo project also includes Argo workflows for orchestrating complex jobs, often used for CI, Argo rollouts for advanced deployment strategies like Blue, Green, or Canary, and Argo events for triggering workflows based on events.
What else is prominent in CI/CD?
Flux is another graduated GitOps tool, providing an alternative to Argo CD. While it's not technically a CNCF project, Tecton, which originated from Google, is a very powerful Kubernetes native framework for building CI/CD pipelines defined as custom Kubernetes resources. And Kepton, an incubating project, focuses on orchestrating the entire application lifecycle, including automated quality gates and promotions based on service-level objectives, SLOs. So a typical end-to-end flow for you might look like this. A CI system, maybe Argo workflows or Tecton, builds your container image. It pushes the image to a container registry like Harbor, which is a graduated CNCF project, providing secure image storage and scanning. That push might trigger Argo CD or Flux to detect the new image tag in Git and initiate the deployment to Kubernetes. Then, perhaps Kepton orchestrates a Canary rollout, watching Prometheus metrics to ensure SLOs are met before promoting it fully. You see how they weave together.
Yeah, that's a great example. The CNCF even runs its own CI system, doesn't it?
They do, CNCF CI. Its purpose is to continuously test the interoperability between different CNCF projects, ensuring that updates in one project don't unexpectedly break integrations with others. That's super important for the stability of the whole ecosystem.
Okay, what about integrating with event-driven architectures, EDAs? That's another huge trend.
Definitely. EDAs rely on services communicating asynchronously by producing and consuming events. Several CNCF projects are relevant here. Cloud Events, a graduated project, is crucial. It doesn't transmit events, but it provides a standardized specification for the metadata format of event data. This ensures interoperability. Different systems can understand the context of an event. like its source type ID, regardless of the underlying messaging protocol.
What about the messaging systems themselves?
NATS, an incubating project, is a very high-performance, lightweight messaging system often used in event-driven scenarios. And Knative, another incubating project built on Kubernetes, provides building blocks for serverless workloads. A key part of Native is native eventing, which aims to provide a universal subscription, delivery, and management system for events within Kubernetes, abstracting away specific message brokers. One big challenge in EDAs is observability, because everything is asynchronous. But OpenTelemetry is critical here too. By ensuring that trace context information is propagated within the event metadata, using the cloud events format, for example, you can actually reconstruct and visualize the end-to-end flow of transactions, even as they hop across different services via message queues.
That's clever. Okay, one last integration area. Running stateful applications like databases on Kubernetes, that used to be a bit controversial, but how has the ecosystem matured?
It's matured significantly. For a long time, people were hesitant, but the tooling and patterns have gotten much better. Kubernetes itself provides the basic primitives: stateful sets for managing stateful pods with stable identities and storage, and persistent volumes, PVs, persistent volume claims, PVCs, for abstracting storage.
What about specific storage projects in the CNCF?
There are several important ones. Rook, a graduated project, acts as an orchestrator for various distributed storage systems like Ceph, deploying and managing them within Kubernetes. Longhorn, an incubating project, provides lightweight distributed block storage specifically designed for Kubernetes. And Tyvee, another graduated project, is itself a distributed transactional key-value database, often used as the storage layer for TDP.
And database-specific projects.
Vitess, graduated, is famous for horizontally scaling MySQL databases, used by giants like YouTube and Slack. OpenEBS, incubating, provides a different take with container-attached storage, essentially turning storage into microservices. But the absolute key enabler for running complex stateful applications like databases on Kubernetes is the operator pattern.
The operator pattern. Explain that.
An operator is essentially a custom Kubernetes controller that you build specifically for managing a particular application. It encodes the operational knowledge, how to do backups, handle failover, manage upgrades, scale the cluster for that specific application, like PostgreSQL or Kafka, directly into software that runs within Kubernetes. It automates those complex application-specific day two operations. There are hundreds of operators available now, making stateful workloads on Kubernetes much more viable and manageable for you.
It really feels like this is more than just code. It's a massive global community driving all this innovation. For listeners who are inspired, how can they get involved and contribute? Is it just about writing code?
Not at all. The CNCF actively encourages contributions beyond just code, which is fantastic. There are many paths.
Like what?
You can obviously contribute code to the projects themselves. Tackling issues, especially ones marked Good First Issue, is a great way to start. But you can also contribute documentation, help triage new bug reports, participate in the discussions within the technical advisory groups tags that focus on specific areas like storage or security. You could organize or speak at local cloud-native community groups, CNCGs. Creating content, blog posts, tutorials, videos is hugely valuable. There are even formal roles like becoming a CNCF ambassador. And programs like the LFX Mentorship offer structured ways for newcomers to get involved with guidance from experienced contributors. There's a place for almost any skill set.
That's great to hear. And what about validating expertise? If someone wants to formally demonstrate their skills in this area, what certifications does the CNCF offer?
The CNCF offers several highly respected industry standard certifications. And a key thing about them is that they are performance-based, meaning you don't just answer multiple choice questions. You get a live command line environment, and you have to actually solve real-world problems, configure clusters, deploy applications, troubleshoot issues within a time limit. They really test practical skills.
Which ones are the main ones?
The big three are Certified Kubernetes Administrator, CKA. This is focused on the skills needed to operate and manage production-grade Kubernetes clusters. Think cluster installation, configuration, networking, storage, security, troubleshooting. Certified Kubernetes Application Developer, CKA. This focuses on the skills needed to design, build, configure, and deploy cloud-native applications on Kubernetes, using core resources like deployments, services, config maps, secrets, etc. Certified Kubernetes Security Specialist, CKS. This is a higher-level cert focused specifically on securing container-based applications and Kubernetes platforms during build, deployment, and runtime. It actually requires you to hold a CKA first. They also have associate-level exams like the KCNA, Kubernetes and Cloud Native Associate, for foundational knowledge, and the CMPA for platform engineering we mentioned earlier. And there are now newer specialist certifications focusing on specific projects like Prometheus, Istio, and Cilium. Investing in these certifications for yourself or your team is definitely a strategic move to validate skills.
Absolutely. And of course, the central gathering point for this whole community seems to be the premier event, KubeCon plus Cloud Native Con.
Oh yeah, KubeCon is the place to be. It's the central hub for the entire cloud-native ecosystem, held multiple times a year in different regions, North America, Europe, China.
What happens there?
It's huge.
Yeah.
You get keynotes from industry leaders setting the vision, multiple technical tracks covering literally everything in the landscape, from deep dives on kernel tech like eBPF to platform engineering strategies to running AML workloads. There are lots of co-located events focusing on specific projects or themes before the main conference, and the networking opportunities are invaluable. Plus, the project pavilion in the expo hall lets you walk up and talk directly to the maintainers of the projects you use or are considering. Attending KubeCon, even virtually, is probably the single most efficient way to get a pulse on the industry, learn about emerging trends, and build connections.
Sounds essential. Okay, so adopting cloud native, embracing these technologies and patterns, it's clearly a significant strategic undertaking for any organization. What are the key considerations when embarking on this journey?
It absolutely requires careful planning and a strategic mindset. It's not just about adopting new tools. It's often about changing processes, culture, and team structures too. A key first step is evaluating maturity, both the maturity of the specific CNCF projects you're considering and, crucially, your own organization's maturity.
We talked about evaluating project maturity using the sandbox, incubating graduated levels as a risk framework. How do you evaluate your organization's maturity for cloud-native adoption?
That's where the Cloud Native Maturity Model, CNMM, developed by the CNCF Cartographos Working Group, which is made up of end users, becomes incredibly valuable.
How does that model work?
It's a 5-level framework, level 1 being the least mature, level 5 the most. But importantly, it assesses maturity across 4 key dimensions: people, skills, culture, team structure, process, workflows, automation, release practices, policy, governance, security, compliance, and technology, infrastructure, architecture, tooling. And critically, all of these are assessed in the context of achieving specific business outcomes.
So it's holistic, not just tech-focused.
Exactly. It helps you understand where your organization currently stands across all these dimensions, identify gaps, and create a roadmap for improvement. And the goal isn't necessarily for everyone to reach level 5 in all areas. Maybe reaching level 3 defined is sufficient to meet your specific business needs and goals. It provides a structured way to think about your journey.
Okay, another huge strategic question that always comes up, the buy versus build dilemma. Should an organization try to build its own internal platform using these open source components, or buy a commercial distribution or managed service?
The eternal question. And there's no single right answer. It's highly context dependent. Let's break down the pros and cons.
Okay, what about building in-house using primarily open source CNCF projects?
The pros are clear. Maximum customization to your specific needs, potentially zero vendor lock-in, and you build deep in-house expertise, which can be a competitive advantage. The cons, however, are significant. It requires a substantial upfront investment in time, often 12, 18 months or more, to build a robust internal platform from scratch. And resources. Skilled engineers are expensive and hard to retain. You also bear the full burden of ongoing maintenance, security patching, upgrades, and supporting your internal users.
Right, and buying a commercial managed service, like OpenShift or EKS Gkeeks.
The pros here are often faster time to value. You get a working platform much quicker. The vendor handles a lot of the underlying maintenance, support, and operational heavy lifting, reducing your burden and often lowering initial risk. The cons are typically ongoing subscription or usage costs, potentially less flexibility or customization compared to building your own, and the risk of vendor lock-in, making it harder to switch providers later. So as the architect, you really need to lead a careful evaluation. What are your organization's core competencies? What's your budget? How fast do you need to move? What's your tolerance for operational overhead versus vendor lock-in? Building might make sense if you have highly specialized requirements or if the platform itself is your core business. But for many organizations, buying a managed service or a commercial distribution often provides a more cost-effective and faster path to realizing the benefits of cloud native, even with the trade-offs.
That's a very balanced view. Now, as organizations migrate, what are some common migration anti-patterns, things people should actively try to avoid?
Oh, there are definitely pitfalls to watch out for. Being aware of these anti-patterns can save a lot of pain.
Lay them on us.
Okay, first, the monolithic lift and shift. This is just taking your existing large monolithic application, sticking it inside a container, and deploying it to Kubernetes without changing its architecture. You fail to leverage the real benefits of cloud native, like elasticity, resilience from microservices, and often end up paying more for cloud infrastructure with very little gain. It's usually a recipe for disappointment.
Right, don't just move the problem.
Exactly. Second, ignoring cost optimization leading to cloud shock. It's easy to over-provision resources in the cloud or on Kubernetes. If you don't actively implement Finex practices, things like cost monitoring, setting resource requests and limits correctly, using auto-scaling effectively, you can get a surprisingly large bill at the end of the month.
Budget responsibility.
Absolutely. Third, sticking with mutable infrastructure. This is continuing the old habit of logging into running servers or containers and making configuration changes directly. This inevitably leads to configuration drift, making environments inconsistent and hard to manage or reproduce. You really need to embrace the immutable infrastructure pattern we talked about earlier. Build new, replace old.
Makes sense. What else?
Fourth, ignoring CI/CD and automation. Trying to do manual deployments to Kubernetes completely negates the speed, predictability, and reliability that cloud native promises. Robust CI/CD pipelines integrated with GitOps are essential.
And finally,
A big one. Organizational silos, sometimes leading to shadow IT. If different teams within the organization start building their own isolated Kubernetes clusters or adopting different monitoring tools without coordination, you end up with duplicated effort, inconsistent standards, security risks, and higher costs. A successful cloud data strategy really requires a collaborative approach, often centered around a shared platform team providing common tools and standards. Avoiding these anti-patterns is key to a successful migration.
that's incredibly useful advice. Okay, looking ahead now, the cloud-native ecosystem, as we've said, never stops moving. For architects trying to stay ahead of the curve, what's on the horizon? What future trends should we be tracking closely?
Yeah, keeping an eye on the future is crucial for making smart strategic bets today. There are several really exciting trends emerging.
Let's start with one you mentioned earlier, the ascendancy of eBPF. Just how big do you think its impact will be?
I truly believe eBPF is one of the most fundamentally disruptive technologies shaping the future of infrastructure. As we discussed, its ability to safely and dynamically run programs within the Linux kernel unlocks incredible performance and functionality.
We saw it with Cilium.
Right. Cilium uses it for high-performance networking and security, replacing older methods like iptables. Falco uses it for runtime security monitoring. Observability tools like Pixie, another CNCF project, use eBPF for automatic application instrumentation without requiring code changes. The clear trend is that more and more functionality that used to live in user space proxies, like sign cards, or required clunky kernel modules, is being pushed down into the kernel via eBPF for much higher performance and efficiency. Expect to see eBPF underpinning even more networking, security, and observability tools in the coming years.
Okay, what about WebAssembly or WASM? There's a lot of buzz around it being the potential next-generation runtime. Is it going to replace containers?
That's the big question. WebAssembly WASM is a portable binary instruction format initially designed for the web, but it's rapidly gaining traction on the server side as well. It offers some really compelling advantages.
Such as?
Near instant startup times, we're talking milliseconds, compared to seconds for many containers. Much smaller artifact sizes than typical container images. A very strong capability-based security sandbox model by default. And true language-agnostic portability. You can compile code from many languages, like Rust, C++, or Swift, to WASM and run it anywhere a WASM runtime exists. The CNCF recognizes its potential. There's a WASM working group, and sandbox projects like WASM Edge and WASM Cloud provide WASM runtimes. Kubernetes itself can now schedule WASM workloads alongside containers using the runtime class feature. We're also seeing WASM used as a plugin model. Envoy supports WASM filters for custom logic, and policy engines like OPA can compile policies down to WASM for efficient execution.
So replace containers or coexist?
For you, the architect, WASM looks incredibly promising for use cases like serverless functions, fast cold starts, edge computing, small footprint, fast execution, and safe, efficient plugin architectures. I don't think it's necessarily replacing containers wholesale in the near future, but rather coexisting with them. You'll choose the right runtime container or WASM for the specific workload, and orchestrators like Kubernetes will manage both. It's definitely a space to watch closely.
Very interesting. And what about the intersection of AI and machine learning on Kubernetes? That seems to be exploding.
It really is. Kubernetes has rapidly become the de facto standard platform for orchestrating complex, often resource-intensive AML training and inference pipelines. The CNCF is now actively hosting projects aimed at building a complete open-source stack for cloud-native AI. A common stack you'll see emerging includes Kubernetes itself for the core compute and resource management, especially managing expensive GPUs effectively. Ray, an open-source framework now gaining traction within CNCF circles, is often used for distributed execution of Python workloads, key for large-scale training. Deep learning frameworks like PyTorch run on top. And Kubeflow, a graduated CNCF project, aims to provide an end-to-end MLOps platform on Kubernetes, covering everything from data preparation and model training to deployment and monitoring. Kserve, formerly KF Serving, an incubating project, specifically focuses on providing scalable, serverless model inference. What this trend really points towards is the potential commoditization of MLOps platforms. It offers organizations an open, portable, and scalable alternative to relying solely on the proprietary integrated AML platforms offered by the major cloud providers. You can build your own best-of-breed AI platform using these interoperable CNCF components.
Fascinating. Okay, finally, as organizations scale and go global, managing multiple Kubernetes clusters becomes the norm, right? How is multi-cluster management evolving?
Yes. As organizations mature with Kubernetes, operating a single cluster often isn't enough. Multi-cluster becomes the reality for reasons like achieving higher availability across regions or failure domains, isolating different environments, dev staging prod, meeting data locality or sovereignty requirements, or simply dealing with scale limitations of a single cluster. But managing a fleet of clusters is inherently complex. The future here is moving beyond simple federation, just seeing all clusters, towards more sophisticated multi-cluster orchestration. The goal is to manage workloads and policies across multiple clusters, as if they were a single logical unit, while still respecting their boundaries. Projects are emerging in this space within the CNCF, like Karmata, Sandbox Project, and Open Cluster Management, OCM, which aim to provide advanced capabilities for propagating applications and enforcing policies consistently across cluster fleets. Service missions like Istio have features for spanning multiple clusters to provide unified traffic management and security. And GitOps tools like Argo CD are essential for managing the desired state across distributed clusters. For you, the architect, you should definitely anticipate needing to operate in a multi-cluster environment sooner rather than later. The key challenge, and where innovation is happening, is selecting the right control plane technologies that can effectively abstract away the complexity of the underlying cluster fleet and provide a unified management and operational experience. So, what we've really explored today, I think, highlights just how profoundly the cloud-native computing foundation has cultivated this vibrant, truly vendor-neutral ecosystem. It's become the bedrock of so much modern software. Its influence goes way beyond just Kubernetes now, encompassing this comprehensive suite of technologies that cover the entire lifecycle: networking, observability, security, delivery, all of it.
Absolutely. And for you, the software architect listening, the CNCF really isn't just a place to find open source tools. It's more like a strategic partner, wouldn't you say?
I think that's a great way to put it.
Its rigorous governance, that transparent project maturity lifecycle we discussed, it offers a reliable framework for you to evaluate technology choices and manage the inherent risks. And those architectural patterns, it champions separating control and data planes, GitOps, the service mesh, the three pillars of observability. These provide durable blueprints for building systems that are scalable, resilient, and actually manageable in the long run.
And the journey, the mission to make cloud-native computing ubiquitous, it's definitely still ongoing. This ecosystem is in perpetual motion, constant dynamic evolution. We're seeing these emerging trends like eBPF really taking hold, WebAssembly finding its place, the convergence of AML happening right on top of Kubernetes. These are poised to redefine the technological landscape yet again. So the core challenge for you as an architect today isn't really if you should adopt cloud-native principles anymore. It's much more about how to strategically navigate this vast, sometimes complex, but incredibly powerful ecosystem.
Success really seems to require that deep understanding of the trade-offs: Istio versus Linkered versus Cilium, buy versus build, manage versus DIY. It requires a commitment to building robust operational practices, maybe through platform engineering, and definitely a forward-looking perspective to anticipate that next wave of innovation. So, thinking about everything we've covered, what stands out to you, our listener, as the most critical concept or pattern from today's deep dive? What's the one thing you'll really take away and apply to your own architectural thinking? Something to mull over. That's all the time we have for this deep dive on the joy of architecture. If you found this discussion insightful, and I hope you did, be sure to subscribe to Joy of Architecture wherever you get your podcasts. That way, you'll stay tuned for future episodes where we continue to explore this fascinating world of technology and architecture. Thanks so much for joining us.